curved the graph is, it eventually looks straight. That's the idea behind local linearity. Why is that important? Well, that means it's differentiable, and that means we can use a tangent line to approximate it locally. So right now we're just talking in 2D, just to kind of orient ourselves to what we're going to be talking about. So this would be the function of the square root of x plus 1 along with its tangent line at 0, right? We can see, okay, a lot of overlap here, but they basically diverge as we go to the left and to the right. Well, as we zoom in, this is what local linearity says. Any curved graph will eventually become straight, which allows it to be different, which means it is differentiable. And as we zoom in, we can see that they actually become the same. Hence the term local linearity. Locally, it's linear. Locally, we can approximate it with a tangent line. So I like starting in this because you guys have done tangent lines before. You did them in Calc 1. You did them in Calc 2 when you were doing Taylor polynomials, because a tangent line is just a Taylor polynomial of degree 1. So there's a couple things I want to point out about the tangent line before we generalize into 3D. So basically what's happening is we're at some point, and then the derivative gives us our rate of change. And then we look at the expected change in our output for any possible change in input. So let's say we've got a tangent line at 3. Okay, there's two pieces that are going on here. So what we've done is two basic things. We've made sure that we've matched the function value at 3. Interesting. And we've made sure we match the derivative at 3. That's what gives it that same shape as the graph. Now, one of the things I want to point out to you, I don't know if I'll be able to get this to annotate or not, but try one more time. One of the things I want to make sure we point out right here, this f prime of 3 times x minus 3, that's the differential. All right, so you watched the video today on the differential. The tangent line and the differential are very, very similar. In fact, the differential is part of the tangent line. What we'll see in 3D, the differential is actually just part of the tangent plane. What you want to think about when you think about differentials, what they're doing is they're approximating the amount of change for a change in input. So we have our general tangent line or first degree Taylor polynomial. Now, again, this is back in 2D. So in 3D, well, we know what a linear function looks like, right? So a tangent plane in 3D would be where we're going to match the function value, the partial with respect to x, and the partial with respect to y. So what that does is that gives us a local approximation of our surface. So if we bring up a function in our calcplot 3D, one of the things we can do, we put on a point here, so you can see my little blue point going along. I can have calcplot 3D add a tangent plane for me. All right, so you can see the tangent plane right here at that point. It's okay that the tangent plane goes through the curve. It just needs to be tangent at that point. And I can move it around and it'll basically move that tangent plane around. Kind of like we were talking about last time, if we get up here at the very peak, we get the spot where we get that horizontal tangent line because both our partials would be 0. But that's what a tangent plane looks like. Basically, it's the same concept as a tangent line expanded into 3D. And that just means we have to account for both the partial with respect to x and the partial with respect to y, which we can see is accounted for right in this equation. Finding it is actually not that difficult, and we'll do one a little bit later together, and then you guys will do one on the worksheet. But all you need is the function at AB, the partial with respect to x at AB, the partial with respect to y at AB, and then the point AB. So the only difference between this and Calc 1 is that you have to do both partials as opposed to just a single derivative. But now that we know how to do partials, this is something that we can do. So I like giving this image because it does a couple things. Number one, it shows a tangent plane right here at the point AB. So this is our point of tangency right there. And you can see this is our surface here. It's some curved surface. So our tangent plane is going to diverge from it a little bit. Okay, well, that makes sense. Now, here's the other reason I like to bring this up. This here, this is the expected change in z value given our partials, but you can see the actual change would be up here. So we're off by quite a bit. But what this is, notice f sub x delta x plus f sub y delta y, that's the differential. In fact, all we have to do is add f of AB to this differential, and we have our tangent plane. So the differential accounts for the change. You add the point that you add the point that you were looking for the tangent plane at, and that's what makes it the tangent plane. So they're not two separate topics. So right here, this part here without the f of AB, that's the differential, because what that does is it approximates the change in function value. Adding this on makes it a tangent plane. It's a plane that can be plotted by itself. That's what makes it have the same function value. And you guys are going to do one in the worksheet that's going to kind of bring this idea home of looking at change. Okay, let's talk a little bit about differentials. So in 2D, so again, we're back to 2D. Remember what I said, the differential is basically the derivative times the change in x. So I want to talk about this. So let's talk about square root of 9.2. I'm not able to annotate on here, so I'm just going to have to go to the board. But I want to talk about the difference between what the tangent line and the differential in 2D. It's the same idea in 3D. All right, so in this case, we're looking at a function. We'll call it square root of x, because we're going to be putting in 9.2. This is how these things work. Well, we locate the derivative first. So this is 1/2 x to the minus 1/2. And what we'll do, instead of evaluating these at 9.2, we're going to evaluate them at 9, because 9 is a perfect square. So we'll do f of 9, which is square root of 9, which is 3. And we'll do f prime of 9, which is 9 to the negative 1/2. That's 1 over the square root of 9, which is 1/3 times 1/2. 1/6. All right. Now, if we were setting up a tangent line, what we would do is we would say, okay, y is approximately f of 9 plus f prime of 9 times x minus 9. Okay. And so now if we wanted to get what square root of 9.2 is, we put 9.2 in for x. All right, well, let's do that. So we've got 3 plus 1/6, and we're doing 9.2, so 9.2 minus 9. So 3 plus 1/6. This leaves us with 0.2, which is 1/5. So I'm just going to keep the whole thing in fractions. And this thing comes out to be 3 1/30. So it's an approximation for the square root of 9.2. All right. Now, this we did with a tangent line. Okay. Here's the way a differential works. So the differential is specifically this part here. That's the differential. So the differential talks about how much we change by. So the differential says, well, hey, if I increase my input from 9 to 9.2, then I'd expect my output to go up by about 1/30. That's what the differential says. It looks at the change in output only. Whereas the tangent plane says the output is 3 1/30. The differential says our output that was 3 went up by 1/30. So they're very, very closely related. So I don't want you to think of them as two separate topics. All right. So the differential talks about our expected change in output. So differentials in 3 space, not complicated actually. It's f sub x times our change in x plus f sub y times our change in y. And shorthand notation, f sub x dx, f sub y dy. All right, so going back to my 2D example, that 1/5, that was our change in x. That would be what we're calling dx. Okay. We can call it delta x too. The reason we're using dx is because we're talking about what happens as these things get infinitely small. All right. So the important takeaway here is with differentials is that A, they're part of the tangent plane. They make up most of the tangent plane. The only thing is we need that anchor point to make it a tangent plane. The other thing that I want you to take away is differentials give an approximate change in output given changes in input. All right. So given a change in our x and our y, we can use the differential to approximate the change in our output. So why would we do that? Well, it gives us a way of measuring our expected change in output, in particular in situations where the functions may not be easy to work with, or we may not be able to work with the functions. Same reason we would use a tangent line approximation. It might be easier to work with than the actual function. Same reason we would use Taylor polynomials, because they might be easier to work with than the actual function and manipulate. Now, just like we learned in Calc 1, the smaller the dx, delta x, the smaller the delta y, the more accurate our approximation will be. We kind of saw that in the picture, right? You know, the closer we are to AB, well, the less error we're going to have. The further out we get, the more error that's possible. Doesn't mean it absolutely could happen. You know, this surface could have curved back down and just happened to hit at this point. But there's a reason that they're called local. Locally, they're good approximations. Globally, they're usually not. So that was our introduction into tangent planes and differentials. Again, Do not think of them as separate concepts. The differential is just part of the tangent plane. It's the part of the change. Any questions about tangent planes or differentials? You guys did great finding partials last time. If you can find partial derivatives, you can do tangent planes and you can do differentials. Okay. So like I said, we're going to get a chance to practice some of those, but
Actually, I think in that section there was also like relative error. Are we going to need to know a bit about that?
no.
Okay.
Now we won't look at it. We might look at like an absolute error. Like, okay, here was our approximation. Here's the actual. What was the error? How much were we off by? But that'd be about it. Don't worry about relative error.
So it's not like going to be a homework problem then?
Nope. Okay, other questions? All right. Now we really get into a very big topic, the gradient. So we're not going to worry about that right now. So far, back in last class, we were looking at finding the rate of change either in the X or the Y direction. Well, that only covered two possible directions, right? As you can imagine, at any given point in a plane, there's 360 degrees worth of directions we can go in. There's infinitely many directions. So we want to be able to find the rate of change in any direction. And that's what we're going to work on today. Now, it can be difficult to find rates of changes in other directions by just trying to look at a contour plot, because it's very difficult to determine what your change in output is with respect to your change in input. You have to do a whole bunch of measurements. Because you're not going along the X or the Y, it gets very, very messy. But it turns out that this can actually be broken down very nicely. This is we're going to go through this because there is something I want to show you in here. All right, so let's say we've got a unit vector, we'll call it U. And this is our notation. This is a notation for a directional derivative, F sub U, with the vector hat on it. This is our old limit definition applied to directional derivatives. This would be a mess to do by hand, but it is going to lead us to something better. And what this will do will give us the rate of change of F in the direction of U, where U is any unit vector. That'll take care of the issue of being confined to just the X or Y direction. I want to take a look at how we can calculate this using a little bit of trig and something we just talked about, because something's going to come out of this that is very interesting. Actually, a lot of things come out of this that is very interesting. I know we don't do a lot of derivations in here, but this one I think is worthwhile. So we'll just start with a plot. And this is going to be our point, AB. And let's say that's our unit vector U. That's the direction, some arbitrary direction that we want the derivative in. Okay. Now we got to match it up with our limit definition. So just like all the way back to Calc 1, H is some arbitrary distance that we're eventually going to let be 0. Okay. So let's just put it to about there. Let's say that's H. And we've got our limit definition. So F in the direction of U at AB is the limit as H goes to 0 of F of A plus H U1, comma. This is just the definition. You do not need to know this, but there's something I want to show you. All over H. Okay. So basically what's happening is we're looking at the change between the output at this point and the output is this arbitrary point as H goes to 0. That's the idea. All right, well, how can we make this something that we can work with? Well, let's get in our right triangle, and we'll call this angle alpha. Now, what we have here are basically our change in x, so dx, and our dy. It's going to be some right triangle trig. You know, we have our adjacent side. So this is h cosine alpha. This is our opposite side. So this is h sine alpha. Now here's where things get really cool. This is a change in output. Okay, great. Why is that useful? Well, remember what we just talked about 5 or 10 minutes ago. The differential can give us an estimate in our change in output. So this thing here can be approximated by our differential of f. That's huge for us. In fact, they're going to be exactly the same once h does go to 0. So limit as h goes to 0 of f sub x dx plus f sub y dy all over h. Now again, this is the numerator. That's just the differential we were talking about last time. What does the differential do? It gives an estimate in the change in output. Well, because these are going, h is going to go to 0, this thing is going to be exact. Now, let's also combine what we put in over here. So limit as h goes to 0 of f sub x h cosine alpha plus f sub y h sine alpha all over h. Something very awesome happens here, right? All the h's cancel. And that is now our limit. F sub x cosine alpha plus f sub y sine alpha. This gets better. We can break this into the dot product of two vectors. Specifically, fx comma fy dotted with cosine alpha sine alpha. Now, some really cool stuff going on here. Number one, this is a unit vector because cosine squared plus sine squared is 1. So the square root of that is 1. So we know the magnitude of this is 1. So this is a unit vector in the direction we were interested in finding the derivative in. That means it preserves direction, but gets rid of the magnitude. So there's our unit vector in our direction. This is just a vector made up of our partials. You know, I'm probably going to say it a few times today. If you can take your partial derivatives, you can find this vector. It's just made up of the partials. There's nothing crazy going on here. X goes first, y goes second. This vector has a special name. Happen to know what it is? Just this vector by itself. I'll give you a hint, it was in the title of this section.
The directional vector.
No, the directional vector is this one.
Right.
That's going to give us the direction. Oh no.
Directional derivative.
Nope, this whole thing is the directional derivative.
The gradient.
That's it. Oh, there we go. This here is the gradient. Never take that long to give me that answer again. Guys, the gradient is as far as how easy it is to find, because it's just a gradient, it's just a vector made up of the partials, it's probably one of the most powerful things that we have in all of calculus. I'm not saying it's the most powerful overall, but with respect to how easy it is to find, it is extremely powerful. The gradient is going to come up again and again for the rest of the semester. So the gradient is part of, now this whole thing is the directional derivative. The gradient is used to find the directional derivative. All right. And all you have to do is take your gradient and dot it with a unit vector in the direction that you're interested in. And we'll do an example of that later. But I just want to kind of really beat home the importance of the gradient. There is a link, and it should be actually, I think it's on today's calendar page, to a website I like called Better Explained. And they have an intuitive approach to the gradient. So if you get a chance, check it out. They have some really cool stuff on their site. I'll link it a little later with some of the other topics that we'll get to that may feel a little bit abstract at first, but are really powerful. So this gradient is going to be big for us. If you can find partial derivatives, you can find the gradient. That's the best part. That's what we worked on. That's why we spent time working on that last time. If we have our partial derivatives down, we can find tangent planes, we can find differentials, we can find gradients, we can find directional derivatives. Everything falls out of that. So if you want everything above this line, you can forget about it. That's fine. It was just to show you where it came from and to introduce you to the gradient. This is what we need to be able to do. All right. Let's talk a little bit about this gradient fella, because like I said, it is a big deal. And when I say it's a big deal, I'm certainly not trying to scare you. It is easy to find and it is easy to use. It's almost like you think it's wrong because it's so easy. So we're going to talk about the gradient by itself, and then we'll talk a little bit about it combined with the directional derivative. Again, it's a vector made up of the partials. That's it. If you can find partials, you can find a gradient, and they go in order. This extends to n dimensions. However many variables you can have a gradient for it. We're only going to do it in 2D and 3D. But if you had a function of 4 variables, you could find a gradient for it. All right. This I wouldn't worry about too much, but it talks a little bit about the relationship between the directional derivative and the gradient. Now, more often than not, this is going to be the form that you're going to see the right here. Yes, the upside down triangle is the notation for the gradient. This is saying the gradient of f at the point AB. So that's all the gradient, and getting dotted with u, where u is a unit vector. That's the directional derivative. So, you know, on the board, I have cosine alpha, sine alpha. Yeah. Oh, oops, I didn't mean to. Thank you. Like we talked about before, very rarely will we do vectors in terms of an angle unless that's what we're given. Most of the time we'll have vectors in terms of components. But all we care about is that it's a unit vector. We preserve the direction, we want to get rid of the magnitude. The next part is if you're dotting it along the x-axis, well, then you get the partial with respect to x. Well, that makes sense. That's the direction you're going in. You dot it with a vector along the y-axis, you get f sub y. Nothing crazy going on there. All right, just a couple properties fall out of this. This was our geometric definition of the dot product. Remember, it relied on the angle between two vectors. Now, we know that the magnitude of the unit vector is 1. So really all it boils down to is the magnitude of the gradient times cosine of theta. Well, that means when theta is 0, these things are going to be at a maximum. That's going to be a really important idea, because that means that the gradient points in the direction of maximum rate of change, because our directional derivative is a maximum if our unit vector is in the same direction as our gradient. Right? So this is how powerful the gradient is. It's the vector that points in the direction of maximum rate of change, whose magnitude is the maximum rate of change. And all we have to do to be able to find those things is find the gradient. A lot of ideas that we talked about are going to come back into play. So that's our max. The min is if they're in the opposite direction, because it's 180 degrees the opposite direction. So if the gradient is the fastest we can go up, then the 180 degree opposite direction is the fastest we can go down, and hence the min. If they're perpendicular, then the directional derivative is 0. And all this should make sense based on the stuff that we talked about before with our level curves. So let's talk about that. So let's say we have a gradient. Well, remember, we said we would want to be moving perpendicular to a level curve to be moving up or down as quickly as possible. The gradient points in that direction for us. It's always pointing in the direction of increasing f. To get the steepest descent, you would just put a negative in front of your gradient and go the opposite direction. Oh, and lastly, remember, if the angle between u and the gradient is 90 degrees or pi over 2, they're perpendicular. Well, remember what that would mean. That would mean we're walking along a level curve, so we have no rate of change. The magnitude of the gradient is the maximum rate of change. That's it. So if you're ever asked to find the maximum rate of change of a multivariable function, you find the gradient and you find its maximum. Like we said before, it's large when contours are close together, the magnitude, small when they are far apart. Guys, this is nothing new. You told me this stuff. So I'm now taking the stuff you told me when we looked at level curves, and we're just applying it to the gradient, which gives us something concrete where, hey, give me a function. Now I can find the direction of steepest descent and what that maximum rate of change is. I'm not going to spend a lot of time on this. All this stuff, and don't worry about taking notes on this. All this stuff applies in 3D as well. The derivation is a little bit messier than what we did up there, which is why we're not even going to bother doing it. But everything else holds. So if you have a function of 3 variables, if you want to do a directional derivative, it's the gradient dotted with the unit vector in the direction that you're taking the derivative. Same exact definition. Nothing changes at all. Except for one small interpretation, but all this is still the same. The max, it still gives the maximum rate of change. The negative of our gradient still gives the steepest descent, direction and magnitude. And finally, again, if they're perpendicular, it's 0. Now, here's one last thing I want to talk about. And we're going to take a look at why this is kind of interesting here in just a second. So when we had a function of 2 variables, the directional derivative is 0 if we're moving in a direction tangent to a level curve, right? We've talked about that because then there's no rate of change. We're not changing height, right? It's kind of like if you're going on a trail around a mountain, if that trail doesn't go up or down, you have no rate of change. Yep. And the gradient is perpendicular to that, because that'd be your way to go up to the next level or down to the next level as quickly as possible. With a function of 3 variables, it is analogous, but remember, we no longer have level curves, we have level surfaces. All right. So in 3D, the gradient gives us a vector that is normal to a level surface. So that's a difference we want to, that we're going to take advantage of. Let's see, on this next problem. All right, so let's do a tangent plane together. There's something I want to show you. All right, I said before, if you can find partials, you can find a tangent plane. Well, everything, you know, if we remember the formula for a tangent plane, f of AB plus f sub x at AB times x minus a plus f sub y minus b. So okay, so if you guys didn't hear John Paul, he said f of 1 comma 1 is 4. Everybody okay with that? That seem reasonable? Okay, so we're already one piece there. We only need 2 more pieces, really. We need f sub x at AB and f sub y at AB. Well, first let's find them. What's f sub x?
Negative 2x minus. Where do you know it's
So
just
the y
negative
drops
2x?
out.
The y will drop out, right? Because it's a constant.
Yeah.
And f sub y is?
2y.
All right. And then we need them at our point, right? F sub x at 1, 1 is, and f sub y at 1, 1 is negative 2. Very good. That's it. We're done. Our tangent plane is z equals 4 minus 2 times x minus 1 minus 2 times y minus 1. All right. That's how quickly we can find a tangent plane if we know how to take partials. That's it. All right. Now, I want to rethink this idea of finding a tangent plane because sometimes this will be useful. What we're going to do is make our function a level surface of a function of 3 variables. Specifically, it'll be the level surface of the function 6 minus x squared minus y squared minus z. And we'll just say when it equals 0. All right. So W, we got 6 minus x squared minus y squared minus z. Now, remember what we were just saying? For a function of 3 variables, the gradient actually gives us a normal vector to the level surface. So we're specifically going to let this be the level surface when this is 0. And what we'll do is we'll find its gradient. Okay, well, we just go through and take the partials. Minus 2x, minus 2y, minus 1. Now, we are going to evaluate this at our point 1, 1, comma 4. So we're going to think of this as an ordered triple now. And we're going to plug that point into here. So the gradient of W is minus 2, minus 2, minus 1. Now remember what that last slide said. The gradient is perpendicular to the level surface at this point. All right, well, that means what we have is a normal vector. We have a point, then we can find the plane in point normal form. Does that sound familiar?
Yeah.
And so that's going to be minus 2 times x minus 1, minus 2 times y minus 1, minus 1 times z minus 4 equals 0. Now, the question could emerge, okay, well, geez, are these the same plane? Well, let's do this. I'm going to distribute that minus 1 So -2 times x minus 1, -2 times y minus 1, minus z plus 4 equals 0. Then I'll add that z over to the other side, right? Just to save a little time, we put the z over. We get the exact same thing we had before. So it's another way of finding a tangent plane is to treat the function of 2 variables as a level surface of a function of 3 variables and finding the normal vector and then doing point and normal form of a plane. Depending on what you're given and what you're working with, one way may be easier than the other. But again, this is really to drive home the point that what the gradient gives us for a function of 3 variables is a vector that is perpendicular or normal to the level surface. And we can see that clearly because it gave us the exact same tangent plane by doing the point normal form. Questions about that?
Not yet.
All right, and I want to do one. Together from the 13.5 worksheet, just to give us a little bit of practice and bring this thing home. We're going to look at number 4 here. And I think a lot of it you guys are already going to be able to do, but I just want to go through a couple of things. So we're going to look at number 4. So while I'm erasing, if you want to start on A, feel free. So we have f of x, y, z equals 100 minus x squared minus y squared minus z squared. It's not a really difficult function. All right, well, if I want to find the gradient at 3, 4, 5, what's the very first thing I'm going to need to find? I'm going to need the partials. So, gradient of f, what are the partials? Okay, so we have minus 2x, minus 2y, minus 2z. All right, now we should be able to find the gradient of f at 3, 4, 5, which is going to be minus 6, minus 8, minus 10. You know, yeah, okay, we could get some functions that might be, the partials might be a little messy on, but procedurally, this is very doable for us. Okay, B wants a directional derivative in the direction of V. Now, we are going to take a dot product. We've already done part of the work for this, but what do we need to do before we take the dot product?
You have to move.
Yeah, we got to normalize the vector V, because remember what we want to do, we want to preserve the direction, but get rid of the magnitude. So the very first thing we'll do is we'll make V a unit vector, which will have the -2, the 3, and the 1. But we have to divide by the magnitude, which is the square root of the sum of the components. So 2 squared is 4, 3 squared is 9, 13, plus another 1 squared is 14. Square root of that. You can't forget that part, otherwise this thing will not come out correctly. The directional derivative is a scalar. The gradient is a vector. Okay, so now for the directional derivative, so f in the direction of u, we have our gradients, so -6, -8, -10, dotted with. So -2, 3, and 1. The 1/rad14, you can keep it in there, you can put it along the components. Again, our final answer is going to be a scalar. 1/rad14, and then remember dot product, just multiply corresponding components. So what do we got? We got 12 minus 24 minus 10. So when all said and done, we have 1/rad14 times -22. So -22 over square root of 14. Like I said, directional derivative is a scalar. That is the rate of change at the point 3, 4, 5 in the direction of V. Questions about B? C, find the maximum rate of change at 3, 4, 5. What do I need to do? What gives me the maximum rate of change? The magnitude of the gradient. So the maximum rate of change is going to be the square root of, because you're going to be squaring them, you don't have to include the negatives, but what do we have? 36, 64, and 100.
Yeah.
So square root of 200.
Yeah.
You want 10 square root of 2. That's it. We're done. Remember, the gradient is that powerful. It gives us all this stuff. A vector in the direction of maximum rate of change. I'll give you a hint. We already have one on the board. What's a vector on there that would point in the direction of maximum rate of change? And think about what just gave us the maximum rate of change.
Oh,
No.
wait, 3, 4.
Is it the gradient?
Very good. It's the gradient. It's just this. It's just -6, -8, -10.
Oh, that's what I meant by F, so.
Well, f sub u was this directional derivative, which came out to be a scalar.
Oh, yeah, sorry.
That's okay. No, these are the differences that we have to get down. That f sub u, that's not a vector. What this is saying is it's the function taking the derivative of the partial of f in the direction of u. Whereas when we label a vector, well, this is gradient. Gradient gets the upside down triangle. Otherwise our vectors always have a hat on them. But again, we actually got asked the same thing twice in this problem. A and B are the exact same question, just asked different, well, have the exact same answer, just asking about this different aspects of the gradient.
Can I ask a question?
Sure.
So conceptually, the gradient of f is a vector found in the function of f, and this vector, the direction of it, I guess I'm confused by, can you just define what the gradient is for me one more time?
Yeah, the gradient is a vector that at any given point points in the direction of maximum rate of change and whose magnitude is the maximum rate of change.
Okay, and then the gradient, the vector will change at every given point. So we get a different gradient for every different point.
Correct.
And the rate of change is consistently changing depending on that point.
Yes.
Okay, all right.
Yes, and let's see, we got, and that's one of the things, if you want on Calculator 3D,
Oh, okay, wait.
you can have the gradient placed on there. Now the gradient's 0 because we're at the top point, but if I move that point around, you can see how the gradient changes depending on where the point is. That red arrow is the gradient that is pointing in the direction of maximum rate of change, and its magnitude is the maximum rate of change. In fact, notice when the point is on a steeper part of the curve, the vector is longer, and if it's more shallow, it's shorter. So you can, that's just on this drop-down menu if you ever want to add a tangent plane or a gradient. You can also add normal vectors and some of the other stuff, but yeah, so that's what the gradient does. And like I said, what's great about it is if we can find partials, the gradient isn't a problem to find.
Got it.
Other questions at this point? Okay, let's try some problems. We'll start with the 13.4 worksheet, do a couple. If we have time today, we'll move on to the 13.5. If we run out of time, we'll do some 13.5 stuff on Thursday. So I will leave you guys online to Professor Todd.